Hey guys, welcome to a new video. In this video here, we're going to see how we can do object detection all the way from scratch with this ZED camera. So we created this ZED camera Python tutorial where we're basically just going to run through a bunch of examples, how we can use this camera, the ZED2i camera, to create a bunch of different real-world computer vision and AI solutions and also projects. So in this one here, we're going to see how we can do object detection in real time with just the ZED camera. I'm going to run through all the code, how you can set it up line by line, and you'll both get an understanding of how you can work with the ZED SDK in Python, open up the camera, specify the different parameters, how you can set up object detection, even tracking on top of that. With the Python SDK and the ZED camera, we can both run 2D object detection and tracking, 3D object tracking and detection of persons, but it could also be an arbitrary object. I'm going to create another video where we can take our own custom ULV8 models, train it on our own data set, export it and use it with the ZED camera to run in real time. Even how we can go from 2D bounding boxes to 3D bounding boxes with ULV8, ULV9 and ULV10 models. So let's just jump straight into it. I've opened up my code editor. First of all, here we just need to import the different modules. I'm just going to zoom in. So first of all, we need OpenCV. So import OpenCV, and we also need NumPy as NP, and then we have our Python ZED.sl as SL. So now we can actually go in and use that for just specifying all of this here. We can go and use the Python ZED SDK with our SL. So this is pretty much it. We can set up our camera. So we have our ZED equal to sl.camera. So this is pretty much just how to create an instance of a camera. If you're familiar with OpenCV, this is how we can create a video capture. Once we have done that, we can set up some initial parameters. So init underscore parameters. So we can specify the image resolution, the unit that we want to get from our depth map and so on, once we want to take it from 2D to 3D. So now we have this here, we can specify the camera resolution. Right now it's just going to autofill it with Copilot. So we're just going to go through it line by line and how we can set up an object detection system with this ZED SDK. You can specify the image resolution, but you can also go with full HD. So you can go with 2K resolution, and you can also just go with full HD. So right now let's just go with 720. Now we can set the camera's frames per second. Again, you can choose between 60 frames per second, 30 frames per second, and 15. So we don't really want to do that here, not really necessary. So right now, let's go in and set our coordinate units. Coordinate units. There we go. And then we have our SL.unit, and then we can set it in meters. So we have all these different units that you can set it in, but this is basically once you take it from 2D to 3D, when it needs to specify either meters, centimeters, inches, and so on. So now we can actually go from 2D to 3D. We can even get the velocity, the position, and also the acceleration of different types of objects and the real world sizes. So yeah, we can also go in and see which of the depth models we want to use. So we can set our init parameters .depth mode. And right now we can set it to depth mode performance, and we can also specify accuracy and so on. But right now we just want to get the maximum performance. So that's pretty much it. Now we can go down and open up our ZED camera. So this is how we can do it with the initial parameters. So error, it will return an error if it's not able to set up the camera. ZED.open, so this is just as we're opening up a video capture with OpenCV, we specify the init parameters. So the image resolution, coordinate units, depth mode, and so on. And that's pretty much everything that we need to have. So now once we have that, we don't really need to specify that. We can go down and set up our object detection model. So instead of our camera parameters, we now just have our object parameters. So we have sl.object detection parameters. There we go. And we also want to apply tracking on top of that. So it's just going to come up with the code because I'm using the GitHub Copilot. Just to save some time as well, we can set it to true. If you don't set it, it's just going to run traditional object detection. But right now we want to run tracking on top of it. So we can also enable mask output. We don't really want that. We can also enable segmentation. Param.enable segmentation. Set that equal to true. There we go. And then we can specify our detection model. So right now they just have a bunch of different detection models. You can check them within the documentation. So here we have object class pedestrian if we want to create a system around detecting pedestrians in a traffic system, or basically just count how many pedestrians are walking one direction or the other. But right now it's going to take a more generic, basically just a multi-class model. So we can call this multi-class box, and we can even specify that we want to use the aggregate model or just the medium in this example. So there's different variations with it, exactly as if you're using YOLO V8 and so on. We have the nano, small, medium, large, and extra large. And again, I'm going to create videos around like how you can take your own custom dataset, fine-tune your own custom object detection, segmentation models, and all of that, even post-estimation models, and use it with the ZED SDK as well. So we can take YOLO V8 models, go from 2D to 3D, detect the velocity and so on of all your objects, and get the real world measurements. So now we can basically just go in and check if our parameters can be set, or basically just set our enable tracking parameters. So if object param dot enable tracking. So if we want to use tracking, we need to go in and set it up. Here we already have this. So we have our positional tracking parameters. There we go. And then we have sl.positional tracking parameters, and we just need to enable all of it now. So set enable position tracking, and we're good to go. So this is pretty much it. Now we can go down and open up our detection model. So it's the exact same way as when we're opening up our camera. So we just have an error, enable it. So right now we can just call set.enable object detection, and that's pretty much it here that we need to do for setting it up. We specify object parameters. Doesn't matter if you're setting up key points for post estimation, object detection, your camera, and so on. It is the exact same way, and that is why it is so easy to work with. So yeah, we're pretty much good to go. Now we have our object detection model up and running, and we can then go down and extract our objects. So our objects would just be equal to our sl.objects. And now we can go in and specify our runtime parameters and our confidence threshold, where it's basically just going to check if the confidence of our predictions are above this threshold. It is going to add them to our metadata so we can extract it later on, visualize it, use it to trigger different systems, and so on. So right now we can just set up our object runtime program. There we go. Object detection runtime parameters. Again, it's just specifying, initializing a couple of different classes, specifying some configurations and parameters, initializing it, and you're good to go. So now we can go down and set our confidence threshold. Let's just set it to 30 right now. So if it's more than 30% confident that this acts like an object, it's going to use that. So let's now go in and create a window for OpenCV so we can visualize our results later on. So we can create a named window. Let's just call it set, and we just specify here window normal. We create a while loop, so while true. There we go, and now I'm going to show you how we can grab the camera. So instead of just calling the video capture dot read, we can actually go in and grab the image just as we're doing here. So set dot grab, and let's now just turn this Copilot off. So now I've just turned Copilot off here so we can go through it line by line instead of just getting all the code right away, because that will not really make it easy to understand. Instead of just seeing the whole code snippet, we need to go through it line by line so you'll understand it on a lower level and be able to do it on your own as well. So right now we just check if the error message is actually successful, because if it's successful, we're able to grab the frame and use it ourselves. So we have our error code underscore code dot success. There we go. And then we can just retrieve our objects. So set dot retrieve objects. There we go. We throw in our objects, and we also throw in our object runtime parameters. There we go. Now we have that, and we can go down and retrieve our image. So we just call im equal to sl.mat with capital M to create an instance of it, and then we go in and retrieve it from our set camera. So set.retrieve. Retrieve image. There we go. And we just specify our image where we want to store it, and we can specify SL view left. You can also go in and specify right if you want to pull the right image. So again, we have 2 frames, one from the first camera and also one from the second camera. It doesn't really matter in this example, but you just want to visualize it on one of them. So let's go with the left one. So now we have that, we can just go down and actually get the data. and convert it to a numpy array so we can visualize it with OpenCV, because this is going to still be a Stereolabs matrix. So let's now go down and act like converted. So imCV, and we set that equal to our image, im.getData. There we go, and that's pretty much it. And if we're able to detect objects within our image frame, we can then go down and check if there's new objects detected. So if objects dot is underscore new. So if we have new objects detected, we can go in and extract them and just visualize them on the frame right now. If you want to use this to trigger different systems, store the results in JSON files and so on, you can always do that, but this is just how you can extract the information. So right now, let's just go down and have an object array. There we go. And we set that equal to our objects dot object list. Object list. There we go. And we can just print the length of it right now. So we're just going to print a string of the length of our object array, and that will be equal to the number of objects that we have in our frame. So yeah, let's just print that to make sure that we are detecting some objects once we're going to run it. And then we can have a for loop just running through all our object arrays, because this is basically just going to be a list of each individual object that we're detecting. So for object in object list or object array, we can take the top left corner. So this is how you can go in and extract the bounding boxes. So our top left will be equal to our object dot bounding box. So I have our bounding underscore box 2D. You can also go in and take 3D, and you'll get the 3D coordinates of your bounding boxes. So this contains a lot of metadata. So it can both contain the bounding boxes, the confidence scores, the class labels for each individual object, but even the 3D information, velocity of the objects, the real world measurements and so on. So all of that, even the tracking parameters, because we're running tracking on top of it now. So all the metadata, all the attributes is going to be added to the metadata, and you can extract it directly in here by just taking the attributes from the object, use it in your own applications and projects. So this is pretty awesome. But right now we just have this 2D. And we take the 0th element of that, because that is the top left corner, and then we also need the bottom right corner. So let's just have an underscore here to make it a bit more readable. So for visualizing it in OpenCV, we need the top left corner and the bottom right corner. So we can do it the exact same way here. I have our bounding box 2D, and this is going to be the 2nd element. There we go. And now we can just draw a rectangle with OpenCV as we're used to. So rectangle, there we go. We specify our image on OpenCV. So this is a numpy array, and we specify our integer here. Let me just scroll a bit up or down. There we go. We take the integer, so we cast it to an integer. This might be a floating value once we just get it directly back from our model. So make sure you act like cast it to an integer. So we take our top left corner, and we're going to take the 0th element of that, because this is going to be a point or like a list of individual corresponding XY pairs. So we both have the X value and the Y value for top left corner, and the same for our bottom right corner. So yeah, we have this one here. Probably just make it a bit easier to read. So there we go. We have our first point, and we're going to take our second point as well. So that will be the integer of our top left corner. And that's going to be the first element. There we go. We can round it off here. Go to the next line. Just have to delete this part. And we take the second point. So that will be the integer of our bottom right corner. I'm not sure why this is so big. There we go. So our bottom right corner, 0th element of that. And we do the exact same thing again. So let me just copy it. And we take the first element of that. And we can specify the color as well. So we have B, we have G, so let's just make it green. So that will be 255, 0, and our thickness here at the end. So I think all the brackets here, all the parentheses should be lining up as well. So here we have the first point, that is correct. The second point, we have the color, and then we also have the thickness. So we should be good to go here. And we can go down and add a label. So a label will be equal to a f string. So we take an f string here, we can take our object, and inside our object, we can just directly extract the label. So instead of L, we need J, so object label. And we can also go in and specify the confidence score. And let's just go in and take the integer of that. obj, just confidence. And I think we should be good to go here now. Let me just check. So we can also have a percentage after that. So we have our object label, and then we also want to show our confidence score, which we cast to an int before that. And we can use OpenCV to put the text out on the screen. So we have our im, CV2, we have our label, and then we just need to specify the position. So let's take the top left corner. Just going to grab the information from here. There we go. And let's just subtract the y direction by 10. So it's basically just going to take the top left corner and then just 10 pixels up above that. So we have our bounding box all the way in front of us, and then we have on top of it the label with our object label and also the confidence score. You can also have the track ID and so on. You can just directly go in and access it from the metadata inside our objects. So now we're pretty much good to go. Let's make sure that we're outside this here. So yeah, we're inside our while loop. There we go. We can just use imshow from OpenCV, and we have our object detection with set, and we specify our image. So that will be our imcv2 underscore. There we go. We can create a if statement, just checking if when we should actually terminate our camera or like a whole pipeline and program once we hit Q on our keyboard. So cv2.waitKey. This is just the standard OpenCV setup that we've done hundreds of times here on the channel almost. And we need ampersand, and we have X, and that should be equal to our Q on the keyboard. So I think we should be good here. So if we hit Q on a keyboard, it's basically going to go inside this while loop. And once we're in here, we just want to break out. We hit Q on a keyboard, we terminate the program. We want to we want to basically just get rid of all the resources, terminate it. So right now for set, we need to disable object detection, disable underscore object underscore detection, and we also need to close our set camera as we're doing if you're opening up with OpenCV as well. So we have close, and the last one here is to destroy all our windows with OpenCV. So we have destroy all windows. There we go. We're pretty much good to go now. We have everything in here. Let's just make sure that this is act like outside our while loop. So we need to put this one indentation in. So yeah, I think we should be good to go now here. We inside a while loop, we check if we're able to grab a frame. We go in, extract all the objects from our object detection model, and everything will be taken care of in the pipeline by just setting these classes up at the top, initializing them with the different parameters. We extract the object, we just have a for loop iterating through all the objects. We extract the meta information, the attributes of it, and we just show it with a rectangle and also our label. So you can use this information to trigger system, store it on list and so on, so you can track the objects over a number of frames, get all the information, store the information in a database, or trigger some different systems based on it. So let's now go up and open a terminal. Let's see if this program is working out of the box. So I have a terminal here with my conda environment. So Python, we have object detection underscore set.py. We should be good to go now. Let's hit enter and see if it just works out of the box. Nope. So here we can see that it is not able to use this resolution. So let me just go up and explore that. Maybe we don't need to specify the resolution. So just found out from the documentation that in the newest version, they actually changed it. So up here at the top, if I just control C it, we see that it actually specified the resolution up at the top. I'll just scroll all the way up. There we go. So we actually don't need to specify this resolution. So just HD 720 unit meter. We don't need to specify the unit either here in this part. So we just have unit.meter, and you can specify all the other different units available. And for the depth mode, we don't have to do it twice. We just have sl.depth mode .performance in the newest version of the ZED SDK here. So now we should be able to go down Python object detection .py. Let's go down and scroll. It's open up the camera. Here we see camera successfully opened, video mode, serial number, everything is up and running. So multi-class. So we can see that this is a misspell. Multi-class. There we go. So our camera is now up and running. We can see the detections. We're detecting a person, even though it's only my arm. If I turn around, we can see we have some electronics here and there. We even have electronics here moving around. So we need to go in and see what classes are like available. It just seems like some very high level ones. Person, electronics, could be some vehicles here and there and so on as well. We have electronics, person, electronics here in the class. That is definitely not electronics, but it works pretty cool. We can see it works in real time. Even though I'm moving around, we don't really lose frames. We have high confidence. Again, we're going to create other videos where we're going to see how we can train our own custom ULV8 models, set up the whole pipeline, do everything custom. But this is very awesome. We probably have around like 30 lines of code here. You have a whole pipeline up and running. You connect to the camera, you set up object detection, even tracking on top of it. You extract the results. You can get all of this information, 2D information, 3D information, everything directly with the Python SDK from ZED. So this is pretty awesome. Definitely go in, test it out on your own if you have the ZED camera, or stay tuned for some of the upcoming videos that I'm going to do, because we're going to both do object tracking, object detection, key point tracking with post estimation, SLAM, visual geometry, all of that. I'm going to cover all of it in future videos, but also just how can you set it up on Windows computer, Jets and Nanos and so on. So stay tuned for those videos. I'll see you guys in one of the upcoming ones. Until then, happy learning.